Today we're going to start chapter 14, and chapter 14 has to do with shifting and adjusting in some way, changing images. So we're going to start 14.1 with translations, rotations, and tessellations. And there are definitely connections between what we're doing in this section and some of the things that we did in our previous section in chapter 12 with our certain types of symmetries, and you'll see those coming through in different places where it feels like I feel like we kind of already talked about that, and we have in some cases, but from a different perspective. So to start with, we're going to define what a transformation is. A transformation is a one-to-one correspondence from a plane to itself. Basically, a transformation takes an image and transforms it into another image. And it can do it in a lot of different ways. We're going to talk about it shifting it, left, right, up, down. Turning it, right? There's those turn symmetry kind of ideas. Turning it, rotating it. We're going to talk about it enlarging or reducing it. And different types of these result in different kinds of images and how they relate to the first image we started with. A one-to-one correspondence is a relationship between two shapes where each feature in the first image is paired with a corresponding feature in the second image. There's some sort of a natural pairing going on. One type of description of a transformation is that it could be an isometry. An isometry is a motion that preserves length or distance. An isometry is something where you take the shape and you could physically pick it up and shift it and move it somewhere, and it didn't actually change the shape. You could talk about the fact that the original place where it was and the image that it was and the changed image are congruent to one another. They didn't really change. They just changed where they were. So we say two geometric figures are congruent if and only if they can be related by an isometry or a sequence of isometries. But isn't every transformation an isometry? And the answer is no. We could manipulate, and not manipulate to not preserve distance, and we can consider that like similar shapes. Let me write that down. So the answer is no. A transformation could not preserve distance and you can consider our shapes that are similar shapes, right? Right? The lengths are not the same. The basic shape of something is, but its actual size is different. So those are the kinds of transformations that we're going to see that would not be isometries. All right, so we're going to actually talk about a first type of transformation, and it's a very simple, straightforward one. It's a translation. So a translation moves every point of an object a specified distance and a specified direction along a straight line. Let me go through all of the bulleted points here, and then I'll show you an image. It's in your notes too, but translations are isometries. Okay, they don't change shapes or sizes of things. They preserve these distances. The original figure is called a pre-image. The resulting figure after it's moved is called the image. Another vocab sort of definitional kind of thing to note is that a translation is also called a slide because it is an action that mimics the motion of a child sliding. And of course, this is your picture that you have in your notes, right? He's shifted where he is. He's slid. He's moved down the slide. right? Moved forward, if you will, towards us and down in his transformation. But he's the same size and shape he always was. He didn't change, right? He didn't grow up while he slid on the slide, not really. So that's preserving his size. That's what that preserving distance is talking about in his context. All right, a few more things about translations. In a translation, the images, right, the resulting figures of all points are determined by the slide arrows. I'll show you an example later. So that all parts move the same distance in the same direction. No distances, angles, sizes, or shapes are changed by a translation. So the image created by a translation is always congruent to the pre-image. One way to represent a translation is with a dot grid. Dot grids are very helpful. They determine the direction and distance of the slide arrow, and then move points accordingly. The reason dot grids are really nice is because they allow us to physically do something with an image that often doesn't require a whole lot of drawing skill, which is really good for me. I don't have a lot of skill in drawing myself. And they provide a convincing, I guess we'll say, a convincing argument that what we ended with really is congruent to what we started with. So here's an example of a dot grid, okay? And because I couldn't get my stuff to show up originally, you guys are going to just have to work with me on showing how this works. So I don't have the image on here, so you're going to write it with me. Your book gives you the image to start with, okay? I just couldn't get it to show up on my stuff. So the first thing I want you to do is I want you to draw from the second down dot to the right dot, like this, third down dot. And there's an arrow on the end of it. So it looks like this. That's that arrow it talked about in the description. We're going to label this the way your book would have normally. It's going to call this X, and this one's going to be called X prime. Okay, so again, nobody's making you figure that out. They actually give that to you in the problem. I just don't have it marked on your paper to start with. And then along the bottom, we're going to create our image. I don't mean image as an image, but our shape. That to be an arrow there. Okay, so the original shape is going to look like this. And this is where we would start. Okay, so this piece right here is called the pre-image. It's just me talking about the vocab. And the direction, the slide over here, this arrow, shows us how we're going to shift things. So what we notice is, from this dot, every point, this point, moves up 2 and right 1. Okay? So we take every coordinate, every corner specifically is the way it's easiest to do it, and we do that with it. We take the corner and move it up 2 and right 1. So I'll try to color coordinate as I go. So if I take this corner right here, and I go up 2 and right 1, that yellow dot ends up right here. That's up 2 and right 1. Let's try orange. If I take this orange dot here and I go up 2 and right 1, I end up here. Let's take the bottom right corner, because we can, not in theory, but in reality, we can connect the dots here in a moment too. So here's my corner down here that's in green, and if I go up 2 and right 1, I end up right here. And notice the yellow and the green dots, they are actually connected with a vertical or horizontal line, right? Or horizontal line segment. So if I'm thinking about my image up here, I'll do it in blue. There's going to be this line. So the line there corresponds to that line there. So this whole line segment went up to here. Let me move one more dot just because I haven't done this one yet. This dot on the original image goes up 2 and right 1 to end up here. And then again, also my green dot and my red dot are joined by a vertical line segment, so they will be here too, the green and the red. And there's that image that's gone from here to here. My yellow dot here, unfortunately, is kind of on both shapes, so it's kind of funny to mark it this way. But if I take the dot from the original, right, the pre-image, and I go up 2 and right 1, I'm here. I'll just color code it with the same yellow so as not to confuse, hopefully, I don't know, here. The yellow and the red are connected here with the line segment, so they will be here too. The yellow and the orange are, so they will be here too. And the orange and the yellow are here, so they will be here too. Okay. So we end up with the same shape, same size, same distances, all of it just physically picked and moved up 2 and right 1, and it lands right here. The shapes that it lands on, the image, could be completely disconnected from the original shape. It could overlap it in some way. This one overlaps a little. It could overlap more than that, but those are our possibilities. So you can see that it is, in fact, an isometry because it did preserve all of my lengths, and I moved it sort of piece by piece. This resulting figure is actually called the image. Just a reminder. So we can represent translations on a dot grid. We can also represent translations with coordinates. So we can explain translations using coordinates from the Cartesian plane. So we've got some images here, some pictures here. There's a blue triangle and a green triangle. The translation shown from O to O prime, that's that blue line or that blue arrow at the bottom, you see? That's actually the same as this piece up here was originally, right? It's showing where the translation is starting and where it's ending and how it's shifting. And that one actually tells you you're going how many right and how many down. What do you see? You go from here to here. How many right did you go? 5. And how many down did you go? 2. So you go right 5 and you go down 2. Well, moving right 5 means taking all of my points and adding 5 to them, right? Because I've actually got a numerical sort of imposing onto my graph. I didn't have that in before. I couldn't really talk about it that way. So where I was before on my x value is now added 5 to it. That's how I move 5 right. And then all my y coordinates, when they shift down 2, means I subtract 2 from my y coordinates. So over here, sort of verbally, I said move up to right 1, right? I mean, that's what I said. Here we just have a numerical representation for it because there are numbers superimposed upon the graph that I'm using because it's the coordinate grid instead. So in general, we can always take the value xy as an ordered pair, and we can talk about adding or subtracting a number from x and adding or subtracting a number from y. So we're going to do an example of that next. Here we have our original shape, right, the pre-image ABC. It says it wants us to draw the image of the triangle under the translation that takes xy to x minus 3 and y plus 2. And then find the coordinates of the labeled points. So it wants us to find A, B, and C under this translation. We can do this in a couple of different ways. We can do it from sort of a visual perspective by thinking about what this is doing to my values, right? X minus 3, how will the shape move visually? Yeah, it will be left 3, and then the y plus 1 will make it move up 1. So that's sort of a visual of what we are doing. So if you want to think about it from that perspective, then you can take each of the individual dots, like visually, and move them left 3 and up 1. So my A value will move 1, 2, 3 to here. That's left 3 and up 1. My B value would be here. And my C value would be here. Okay, so that's moving them sort of component-wise from a visual perspective. We would draw the resulting triangle, and then we would give our answer by counting where we are for A, B, and C from the pre-image to the image. So this would be A prime, this will be B prime, and this will be C prime. Another way that we could do it is we could see where A, B, and C already are. Right? For instance, like B is the point 1, 4. Right? So B is 1, 4. And we could physically subtract 3 from the number 1 and add 1 to the number 4. Because that's what that actually says back in the algebra component that we were given. Subtract 3, add 1. So if I subtracted 3, I would get -2. If I added 1, I would get 5. And sure enough, that's exactly this point, -2, 5. Okay? So either way, we'll do the same thing. You're just thinking about it from a different perspective. We do need to list them because that's what it indicated in the directions. I need to say what is A prime, B prime, and C prime. So we just found B prime. It's -2, 5. Either from the image I drew in blue or from calculating it based on the numerical components, what is the ordered pair for A prime? It's -4, 2. And how about for C prime? Yeah, it's the origin. It's 0, 0. Okay, any question on that? Because we're about to shift topics especially. Okay, so all of that's translations. Shifting up, right, up, down, left, right. That's what I meant to say. Shifting things. The next type of translation or transformation after translations are rotations. Rotations are a motion of the plane determined by holding one point, called the turn center, fixed, and rotating the plane around this point by a certain amount, called the turn angle. You have to specify the direction, clockwise or counterclockwise. The turn angle is the amount by which all points are rotated along a circle in a specific direction. We've seen some of that terminology before. We saw it when we talked with symmetries. In particular, at that point, we were talking about rotating things so that the image and the pre-image were exactly the same, right? I spun it somehow and it looked exactly like it did before I did my spin, right? Here we aren't necessarily looking for them to be the same. We're just looking to identify what spin, what turn angle was used to get that new image. One way, this is not how we're going to focus on doing things, but one way to talk about rotations is from the perspective of tracing paper. I think this is a pretty good visual. It looks weird on the second diagram, so let me explain what's going on. You see the triangle ABC on the left, and you see that blue dot, right? That blue dot is going to represent our turn center. It's where we're turning things from. The reason I want to mention that is because your turn center doesn't have to be on the object itself. You can be rotating something by a point that's not on your object, and this would be an example of that. Now imagine that we did rotate things about, say, point C. So we held C fixed and we spun it. C would never move, right? But if we have the point off of our image itself, then every point actually ends up moving. Okay, there's not one that's better than the other. They're just two different ways of turning something. You can turn something from a point on the object or from a point not on the object. And you can see how that paper is shifted, right? So like if you imagine that off yellow color, whatever, beigey color, is your tracing paper, and you were to hold the center, turn center fixed, and you were to shift it, the original triangle doesn't move. It's just the image that we're shifting, right? It's the shape and the size and so forth. It gets moved, and it doesn't change the size or shape. So a few details about rotations. In a rotation, the entire shape is picked up and turned. So this really should say the entire pre-image. That would be better. Or just say shape, so it's not confused with where it ends. The entire shape is picked up and turned all at the same time. So because we're shifting the shape all at the same time, much like with translations, no distances, angles, sizes, or the shape itself is changed when we change the pre-image into the image. Because of that, a rotation is called an isometry as well. It preserves those distances. If you rotate something 360 degrees, that's an identity. So every now and then people use that word that phrase 360 degree rotation, and they use it incorrectly. So if you think about like a car accident where someone says, I spun my car 360 degrees, they might be using it right, which would mean they spun the car all the way around and are pointed in the direction they were originally going. Or what they might accidentally have been meaning to say was 180 degrees, because that's it's misspoken a lot. Okay, so 360 degrees means spinning something all the way around from where it was. That's an identity. Specifically, a 180 degree rotation has another name. It's called, oh, is it on my screen? No. It's also called a half turn. And there's a few images here of sort of what a half turn is. Again, some of the, all these images have the turn center not on the shape. So we have our original guy standing up there. He's sort of drawn in the black ink right here. Oh, you've got the wrong color going on. And if you rotate him around this turn center right here, he's standing on his head, but he's not standing on his head in the same position, right? Because the turn center was some distance to his left, so now it's almost like he does a cartwheel onto his head, kind of an image. Okay? So that's his turn center. It's not on his body. If the turn center was on his body, say right here, we'd have the same image drawn upside down right on top of itself. That would be the image. The second one here, you can see kind of like a flagpole. That's kind of what it looks like if you connect the dots anyway. We've got this image, pre-image here. And if it's rotated, it was sort of looking like it was standing up, and now it looks like it's sort of going down into the ground over here. Also over here you can see that we have like a mound on top of the earth, if you will. And when we do the pre-image and we do the rotation, then the image flips and it comes over here, and now it's a hole. Okay, so those are all 180 degrees or half turn rotations. For some nice rotations, like 90 degrees, a dot grid really works pretty well. 180 degree rotations, a dot grid works really well. For a lot of rotations that are not nice, dot grids are really challenging to do your rotations on. So we're going to do an example of one that's not so bad with a dot grid so you can see what I'm talking about. Okay, so here's our pre-image. Got a bunch of dots, right? Our turn center is actually on our object here. It's the corner, it's that little blue mark. On your paper, it's letter O, right? So we're going to take the pre-image here, and we're going to rotate it. And it says that we're going to rotate it counterclockwise. So counterclockwise means this way, right? That's important, because if you go this direction, your image will end up different than if you went this direction. So we're going to rotate it counterclockwise, and we're holding this point fixed. So I'm going to take one point at a time, much like I did on our earlier dot grid problem. I'm actually going to take this point right here. So right now, this point was on a line segment that was horizontal with my blue dot, right? And if I rotate it 90 degrees counterclockwise, it will now be a vertical. Are you with me? So that yellow dot moves up here. You could think about the line segment itself moving from here to here. Okay, so this segment moves up, and there's that 90 degrees. You can actually see it marked on this particular one since I started with that corner. All right, let's take another dot, in particular one that's the second easiest one maybe to do here, and that's this point right here. This dot right here, and the corresponding line segment that goes back to O, is a vertical line segment. And if it's rotated counterclockwise, 90 degrees, vertical will become horizontal. And it will horizontally rotate like this, so that it's actually going to land on the yellow dot that I already have, right? So that pink dot is now becoming my pink dot here, and this piece, which was previously highlighted in orange, is now located here. So in other words, I've taken this whole orange corner and it's rotated up and it's now right here. These pieces are harder to do, all right? But they're easier if you think about their relationship to the points I already plotted. So this one was horizontally, or it was vertically down, and it's shifted to horizontal, right? But this one has to rotate another 90 degrees. Now it was horizontal, so it's got to rotate up to being vertical. It's got to go right here. So this horizontal piece from the pink dot to, in fact, we'll go all the way out to the corner, which is my orange dot over here, all the way over to here. This horizontal piece has to rotate up from the pink piece to being vertical, so it's going to extend up right there. We'll go with green. So it's going to extend like this, landing here. And I've actually plotted all my dots, right? All the corners, the vertices, right? They're actually already plotted. So you can actually see that this orange dot down here and what was previously underneath here, I think a pink dot, I don't know. I think it was yellow to begin with. I've changed my colors several times at this point. These have to be connected, right? And this point moved to here, so that last connection is between these two. So the image that the resulting image that I get is right here. So this piece rotated up to here. Now I'm going to shade them in because it's easier to see since I've got so much color on my screen at this point, trying to move things one piece at a time. This was my pre-image. Okay. Trapezoid, agreed? It's a trapezoid. It's sort of like a long trapezoid. That's what it looks like. And I have shifted it, rotated it specifically, and now it's up here. And now it kind of looks like a tall trapezoid. Okay, so if it's hard for you to visualize moving things piece by piece, and they are sometimes hard, the more complicated the image, the more difficult it is, you can use tracing paper to get a better perspective on it, right? You could do it very much like it talked about over here. Well, what would you do? Well, you could put a piece of paper on top of my original, what's my now blue, my blue shape, and you could draw that image. You could hold that corner O fixed, and you could do the rotation 90 degrees, and you should be able to see what happens and where things land if you want to go to that sort of perspective to draw it as well. Any questions on that? Okay. So the next portion of material here actually was originally not in this section. There was a separate section of material and they merged two of them. Oddly enough, it was the end of this chapter. So this is the first time I've taught it in this order, so that's a little bit different. And what we're going to talk about are tessellations. Tessellations, another way of thinking of them is like tilings. So you've seen tile everywhere. Brick is a form of tiling. Anytime you see tile on the ground that you're walking on, that's a form of tiling. So a tessellation of a plane is a way to fill up the plane with copies of congruent figures so that there are no overlaps or gaps. And in all practical purposes, we sort of ignore grout lines if you think about tiling, okay? So the images on this screen show some tessellations. The first one's just an easy square grid kind of thing. The second one almost looks like subway tiles, right? They're rectangles. The two at the bottom, the first one is triangles, and then the second one is hexagons. Specifically, regular tessellations are any tessellations that are done with regular polygons. And if you'll remember from our previous work, the word regular means that they have all congruent sides and all congruent angles. So our regular tessellations on this screen are in fact this one, because those are equilateral triangles. This one, because they are regular hexagons, but also this one because they are squares. So there's only one on this picture, or one picture on this slide that's not a regular shape, and it's the rectangle. It's important to notice that not all shapes actually tessellate the plane. So you cannot decide, for example, that you really love heptagons, and you're going to find some heptagon-shaped tile and make that work. Maybe it does, maybe it doesn't, but you can't randomly decide that. Not all shapes work. What has to happen is the following. Since the sum of the angles at each vertex must be 360 degrees, the number of angles at each vertex must be 360 degrees divided by the angle measure. Thus, angle measures for these polygons must evenly divide 360. And of course, not all numbers evenly divide 360. So we're going to do example 1 and then we're going to pause for today. Example 1 wants us to take our regular polygons. Now we have regular polygons of all shapes and sizes. We determine our polygons based upon their number of sides or angles, right? So a polygon, the side's 3, that's a triangle. And then we have quadrilaterals, and then we have pentagons and hexagons and so forth. We have all these different shapes. So let's actually talk about the shapes that we have, and we'll start talking first with the triangle because it's the smallest. So a triangle, specifically equilateral, otherwise it's not regular, has 3 sides. And we already drew the image above, or it was drawn for us, that if I take 360 degrees and I take my 3 sides, what are the angle measures in a triangle that's an equilateral triangle? They're 60 degrees. My 3 sides are 60 degrees each. So I would divide by the angle measure. Does 360 divide evenly by 60? Yes, it does. And when I do that, I get 6. And it checks out. That is my smallest regular shape. So we'll go up from there. Now we're going to go to a square. A square has 4 sides. What are its angle measures? Yep, they're 90 degrees. Will 360 divide by 90? Yes, what does it give me? 4. So it works. Do you guys remember if we do a regular pentagon? It's 5 sides, right? Do you remember how we determine the angle measure? That one's probably not one you remember. Do you remember how we determine it? Okay. We take the number of sides, 5. We subtract the number 2. It's always the number 2. We multiply by 180 degrees. This had to do with changing the shapes into triangles. And we divide by our 5 sides. So we had a formula. This happened in chapter 12. So 5 minus 2, of course, is 3. 3 times 180 is 540. 540 divided by 5 gives me 108. Okay, everybody good so far? That angle measure, our question is, does 360 evenly divide by that angle measure? No, this is not a whole number. So what that tells you is that there's no pentagon that will tessellate the plane. I cannot do a tiling in my bathroom with pentagons. I mean, I can't. It's not possible. This one, I'm just going to shrink it up just a little bit so I can go into the hexagon. A hexagon actually works. So with a hexagon, you have 6 sides. And what's the angle measure for this for the hexagon? Do you remember? It is 120. So it'd be 6 minus 2 times 180 divided by 6. It is 120. And if I did 360 divided by 120, does that evenly divide? Yeah, it does. So that gives me 3, so this one works as well. We could keep working our way up. We could try a heptagon, we could try an octagon, we could try a nonagon, we could try a decagon, and we could keep working our way up. What you will find is there's not anymore. They will all turn out like the pentagon, the rest of them will. There are only 3 regular shapes that tessellate: an equilateral triangle, a square, and a hexagon. Nothing else will tessellate and tile an entire plane. So we'll talk about what we do when things aren't one of those shapes that still allow us to tessellate, because we can, they just aren't regular shapes that we will have as well. And we'll pick up there next time.